Hello. In this lecture, we will talk about traveling salesman problem. The merchant leaves his city. He wants to reach all other cities by the shortest, cheapest, fastest road possible and return to his city. So what is the situation? There are some cities. There are some roads. And his goal is to start in his city and visit all the cities in this district, let's say, and come back to his original city. So, what is this red road? This road traverses through all the vertices in the graph and come back to the original vertex. So it's a closed trail that starts and ends at the same vertex and goes through each vertex in this graph. So it's Hamiltonian circuit. So in the previous problems, we thought about Eulerian graphs. In this problem, we will focus on Hamiltonian graphs. So traveling salesman problem in graph theory language. We start and end at the same vertex. We are looking for a closed path that contains all the vertices in the graph. And we want the path to have the smallest possible sum of weights. So as I told you, we are looking for Hamiltonian circuit. So let's try to solve such a task. We need to plan the road for the salesman. Let's say we start from vertex A. We need to visit all the cities and come back to the vertex A. We need the road to be as short as possible. How to do it? So the easiest idea is to find all the Hamiltonian circuits in this graph and then choose the shortest one. What is the number of Hamiltonian circuits in such a graph? So let's write them. We can go, for example, around. So first circuit will be A, B, C, B, and A. Please note that this circuit in opposite direction, so I will write it A, B, C, D, A, is exactly the same circuit as we write above. Why? Because we traverse exactly the same edges. So we are not focusing on the direction, but on the edges we traverse. So another option, for example, like that, we can go from A to B, and then this way to D, C, and A. Okay. And third option, A, D, B, C, A. So maybe I will show on the picture. So it will be like that. Okay. And this will look like that. Okay. So let's do the comparison of the lengths of Hamiltonian circuits. So we have these three circuits, and these are the calculations of the lengths. So for example, this round circuit will take 18, let's say, kilometers, okay? This will take 17, and this 19. So what is the best option for this merchant? Of course, to choose this option. So it might seem that the problem is very easy. We just need to write down all the Hamiltonian circuits and just choose the shortest one. So what is the problem? Imagine that our map looks like this. It's complete graph K15. So we have 15 cities. Let's say here is our starting point, and we need to plan the road for the merchant. What is the problem here? The question is, how many Hamiltonian circuits does the graph K15 have? So this is this number. Okay, why? Because we have 15 vertices. From vertex A, we have 13 edges. So we have 13 options to traverse. Then 13, 12, and so on up to 1. But some circuits will be calculated twice. So we have 14 factorial divided by 2. And this number is bigger than 43 billion. So imagine how many cases we would need to analyze to answer the question how to appropriately plan the road for this merchant. So this is very big number. And here is the table where I've presented how this expression increases for the following n. And as you can see, for small n, it looks quite nice. But for 20, 25, 30, the numbers are enormous big. So the biggest problem is the drastic increase in the number of cases for a larger number of vertices. As you can see here, these are absolutely enormous numbers. So to sum up, a significant increase in the number of calculations relative to the number of cities, as I've showed you on the previous table. Is it good to know whether the graph under consideration is Hamiltonian at all? Very important. An approximation algorithm can be used, which will not necessarily give us the optimal solution. So from this part, please remember that in practice, we normally use some approximation algorithm. They are very good, but we cannot be sure that this gives us the best possible solution. Okay, that's all I've prepared. Take the quiz and see you in the next lecture.